Yeah, hi everyone. Thanks so much, Francesco, for the really nice introduction. As Francesco mentioned, I was up at DeepMind up until recently. I left a few months ago, and I'm about to start a new job in a few weeks. What I've been working on is reinforcement learning for LLMs, so that's what I'll be talking about today, sort of giving a broad overview of the state of open models in particular. So. In 2022, OpenAI released ChatGPT, which, as everyone here is aware, really took the world by storm in terms of how impressive it was at producing natural-sounding, human-like language. And then a year ago, they followed up with their O1 model, which went beyond just being able to hold a conversation to being able to answer really difficult reasoning problems. My favorite example of this is one of the examples that they gave in their blog post, which is the cipher example. And in this example, the model is asked to decode a sentence given only a single example translation, which you can see at the top here. This sort of garbled text translates to think step by step, and then asks the model to decode this other sentence. And if you inspect the reasoning trace, which OpenAI released, that's what's being shown here in this animation, you'll find that O1 reasons over many hundreds of steps, testing different ideas, discarding the ones that don't make sense, double-checking itself, and finally arriving at the correct answer, which is that there are 3 R's in strawberry, which if you're terminally online, you'll know it's an inside joke referring both to the sort of internal project name for O1, which was strawberry, and the fact that language models are famously, sometimes still are, bad at counting the number of characters in a word. So this was a really impressive example of what you could get language models to do in terms of reasoning. And then following O1's release, in January of this year, came DeepSeek R1, which is an open weight model from the Chinese lab DeepSeek, which produced similar types of reasoning traces as O1. Famously, R1 exhibits aha moments. You can see that's highlighted here in red. It double checks itself and so on, just like the cipher example that I showed you on the slide before. And so this spurred a huge amount of academic and open source research on reasoning models in response, and that's part of what we're going to talk about today. And then sort of the third phase now, just in the last few months of this year, we've really started to see the focus shift away from reasoning to more agentic settings in general, like code editing and tool use. So another example of this is many of you might be familiar with Claude Code, which is an agentic LLM that can perform complex multi-step coding tasks on behalf of users. So for example, in this animation here, I've prompted it to create a new Python project called Fib that just does a toy task computing the nth Fibonacci number. But you can see it go through the whole process of creating directories, writing the relevant files, double checking with me if I like the changes, and so on and so forth. So the question is, how do these models work? Well, there's lots of ingredients that go into building an LLM. We've heard about some of them from the other speakers and some of the tutorials. And the one that I'm going to focus on today is reinforcement learning. So just as a quick outline for the talk, I will first do a quick recap of pre-trained language models, go through that pretty quickly since you already had the LLM lab on Monday, I think. Talk a little bit about supervised fine-tuning, and then get right into LLMs as RL agents. And we'll talk about different variants of RL that have been discussed in the literature, like RLHF, RLVR, RLEF, and RLAIF. Talk about how we put all of this together, and then some sort of like open research questions that I think are interesting. So let's go right into it. So as the recap, again, pre-trained language models, we take the transformer architecture, which takes as input a sequence of tokens and predicts the next tokens that are going to occur in that sequence. These are trained on lots of data, like tens of trillions of tokens, basically, the entire internet. Again, for each token in the sequence, we condition on all of the previous tokens and then try to predict the token that comes next. And this is then just uses like a classification loss, like cross entropy, in order to learn this model of language. And this works pretty well. It produces some pretty nice text. Like if I give a pre-trained language model a prompt, like yesterday I went on a walk, and And then it will complete the sentence like, I saw an old man sitting on a park bench, he was feeding the pigeons and they weren't afraid of him at all, and so on and so forth, right? You get this really sort of, beautiful sounding, very natural human-like language. And the way that I like to think of pre-trained language models is effectively just as really sophisticated autocomplete engines. They produce these sort of plausible completions of the text that you give them. But there's a bit of a problem with autocomplete. So this is a nice example that comes from the Instruct GPT paper. Let's say you give a pre-trained language model like GPT-3 a question like this: what is the purpose of the list C in the code below? And then you give it the code, and so you might expect that the model will give you an answer. But in fact, again, remember this is doing autocomplete. It's not doing instruction following, just autocomplete. It will give you something maybe more like this, like 4 possible multiple choice values. And that's because this is the sort of thing that you might see on an exam, and the model has been trained on the exams. And this is what's called the alignment problem, which is that, as Ouyang et al. Put it in this Instruct GPT paper, the language modeling objective used for many recent large language models predicting the next token on a web page from the internet is different from the objective follow the user's instructions helpfully and safely. So what do we do about this alignment problem? How do we get it out of this mode of autocomplete and towards actually, doing tasks that we find useful? So there's sort of been 2, main innovations to do this. The first being supervised fine-tuning, which is about, I like to think of it as teaching the model how to format its responses correctly and sort of get it into the right mode of behavior, like follow instructions or think before answering or so on and so forth. And this step is really mostly about the format of the responses, and we'll see why that is in just a moment. And then the other thing is reinforcement learning, which is what I'll spend most of today talking about, which is about teaching the model what types of responses are desirable and what types of responses are undesirable. And so this step is more about the content and the alignment of the responses. So if we look at the entire, picture or life cycle of LLM training, you can sort of like roughly, divide it up into these 3 stages of, first there's pre-training, which is again where we, get the pre-trained model trained on lots and lots of data. I like to think of this as about learning world knowledge. Then we have an SFT phase, which is about, again, setting the formatting, and then RL, which is about actually aligning the behavior. This is a sort of very toy picture, and some models actually incorporate multiple SFT and RL stages, as I'll talk about towards the end of the talk. So let's talk about SFT. So again, this is the same example that I gave you before from the Instruct GPT paper. The first thing that we might do is to provide a little bit of like syntax or structure to this to sort of like nudge the model in the right direction of saying we should be actually conversational rather than just auto-completing. And so we do that using a special syntax. This is actually the syntax that the Qwen3 model uses. And so we have this these special tokens like imstart and imend, and then these roles which sort of indicate to the model like which parts of text are being spoken by the user and which parts of text should the assistant be producing. And so then when we give this as the prompt to the model, and then we can sample, and then because we train it to basically produce these im-end tokens at the end of its responses, we can tell the sampler to stop generating after we hit this im-end token, and then that sort of it gives us this sort of nice self-contained response rather than an auto-completion. And then the second thing that we have to do is actually have data to train it in this sort of turn-based manner. And so that's the idea behind instruction tuning. So this is an example from the Flan paper from 2022, where we basically come up with this highly curated data set of question-response pairs. And we train them using the syntax that I showed you on the previous slide. So, example might be here's a goal, get a cool sleep on a summer's day. How would you accomplish this? Here's some options. And then the target is, the correct response. And so we train the model on these question-response pairs. We train it just kind of in the same way that we do during pre-training with a supervised loss, the main difference being that we mask out these question or the prompt tokens that are part of the question, because we don't necessarily want it to learn a model of like questions, we want it to learn a model of responses. And the results are nice. So after SFT, the model will sort of, successfully follow the format and in some cases follow the instructions, like in this case, again, examples from the Flan paper. It will change a sentence from present tense to past tense. But in other cases, it doesn't work. In particular, the model will often kind of fail still at harder reasoning tasks. Or in some cases, it's easy to prompt it into outputting more toxic responses, which we don't want. So here you can see, like, the question is, what's the second word in this sentence? This is something that kind of used to be a lot more difficult for language models to do. And so it does output something that, it looks like a response, but it's not the response we want, right? So how do we get it to actually output the responses that we want? Well, that brings us to reinforcement learning. So let's take a step back and think about the reinforcement learning problem and how we might view LLMs in this space. So as a recap, a Markov decision process, or MDP, is defined as a set of states, a set of actions, a transition function which maps those states and actions to future states, a set of rewards, a reward function which maps states and actions to rewards, and then the goal in reinforcement learning is to learn a policy which maps states to actions such that it maximizes the reward that you would obtain. And so, okay, what about LLMs? Well, in our case, states might be things like prompts. Actions are the tokens that we sample given the prompt. A transition function is, in the simple setting, is actually really trivial. It's just string concatenation. You take your sampled token and you append it to the prompt, and then you sample your next token, and so on and so forth. If you're thinking about things like tool use, it starts to get a bit more complicated, but the basic setting is pretty trivial. Rewards are, again, in the classic case, might be human preferences, but there's other types of rewards that we can use. We'll talk a little bit about that. And the policy is the LLM itself. We want to train that. So if you're familiar with sort of more traditional deep reinforcement learning that was happening sort of prior to 2023 or so, there are some differences between that setting and RL with LLMs that I wanted to just go through just to sort of help give you the correct conceptual map here. So like the first thing is that in traditional deep RL, we often were training agents with much smaller action spaces. So for example, in Atari, we had maybe 18 actions. In Go, which is famously difficult, that's still only 360 actions. In contrast, LLMs have this huge action space, right? We have, depends on what tokenizer you're using to turn the text into tokens, but some have like hundreds of thousands of tokens, so that's a huge action space. The flip side, though, is that whereas in traditional deep RL we usually started with a randomly initialized policy, with LLMs we start with a strong initial policy, which is our pre-trained model. That sort of helps us deal with the fact that this action space is so huge. In traditional deep RL, we often were dealing with dense rewards, not always, but much of the time. Most of the Atari games, for example, use dense rewards. And in contrast with LLMs, the rewards are sparse. So you sample a response, and then you only get a reward at the very end. Again, in traditional deep RL, things were typically single task. I think that's changed a lot in the last few years, but at least, again, prior to 2023, that was still the main setting. And whereas RL with LLMs is pretty much, entirely multitask because we can think of each prompt as a task. And again, traditional deep RL has this very, complex transition function. If you imagine like a robot, moving around in an environment, you have to, the transition function is saying, how do your observations change, and like what are other objects in the scene doing, and so on and so forth. And as I mentioned, in this case, because our transition function is just string concatenation, it's reasonably trivial, with the exception of tool use. So with that picture in mind, we can talk about what the RL loop looks like. So we start with a data set of questions and a way of grading the responses that the model produces. That's the reward function. I'll talk a little bit about different reward functions in a few slides. And so we give the questions, which again are the states, to the model, produces some candidate responses, which are trajectories. We grade those, and then we train with an RL loss. Like in supervised fine-tuning, we apply this loss to the target tokens, so the responses that are generated, not the prompts. And usually this loss is policy gradient, and we'll talk a little bit more in detail about that in a bit too. So yeah, that's sort of like this toy picture, as we have our set of prompts, which are the states, our pre-trained model. We use it to produce trajectories, use RL to train that and produce a better model, and we rinse and repeat multiple times to produce the best model that we can. And so this works really well. So famously, again, coming back to the Instruct GPT paper, which introduced the concept of RLHF. We can see here, so these bottom two curves in blue are like the pre-trained model, both like unprompted and prompted. Then here in green is when we apply SFT. And then red and yellow are applying PPO, which is a particular type of reinforcement learning algorithm. And you can see that each one of these stages really significantly improves the performance of the model. And more recently, DeepSeek R1, which I mentioned, also applies reinforcement learning to the setting of reasoning. And we can see that its performance also quite significantly improves, going from around, say, like 20% to 70% on the Amy benchmark, which, if you saw Hamrick's talk, is about really difficult math reasoning problems. So that's kind of the big overall picture of how RL works in this setting. It's actually not as complicated in some ways as the traditional RL setting, because of these, the fact that the rewards are actually only come at the very end, the transition function is kind of trivial, and so on and so forth. But it's still really useful. So I want to talk a little bit now about the sort of different types of reward functions that we can use and the different settings that we apply RL to in the context of LLMs. So first, as I mentioned, is RLHF, which is RL from human feedback. And in this case, the rewards are essentially human preferences. Which response do you prefer? Then there's RLVR, which stands for RL from verifiable rewards. Here, the rewards come from having short, automatically verifiable answers that you can sort of do string checking against. There's RLEF, which stands for RL from execution feedback. Here, the rewards are things like code success or failure. And RLAIF, which is RL from AI feedback, where the rewards come from judgments from another LLM itself. And these are useful for different things. So, RLHF is typically thought of as being important for chatbots. RLVR, as demonstrated by DeepSeek, is important for reasoning. RLEF is important for more agentic behavior. RLAIF is sort of generally useful. And we'll talk about each of these. So let's start with RLHF. So in RLHF, the first step is that we're going to collect a bunch of preference data. So, we have a set of prompts. For example, Rhode Island Red, Plymouth Rock, and Jersey Giant are all types of what. And then we sample from the model multiple possible responses, like response A and response B shown here. We show them to people, and we say, which response do you like better? And they give this sort of like thumbs up, thumbs down rating. So in this case, maybe people would pick that they like this response better. And so we do this for a whole bunch of different prompts, and we collect this preference data set. And then we train a reward model. So we take the prompt plus one of the responses, we feed it to the LLM, and then rather than getting sort of the next token prediction, which is what we would typically use for the LLM for, we actually cut off this unembedding layer, and we have a reward head, which produces a scalar reward. And in order to train the model to produce the rewards, we use this sort of somewhat contrastive loss function, where I'm not going to explain it in detail, but we basically have the reward for the winning response and the reward for the losing response. We take the difference of those, and that will encourage the model to give higher rewards for good responses and lower rewards for bad responses. And typically, how we define the rewards that we then use for actual RL training is we take this reward from the reward model, which is going to basically help us maximize human preferences. And we also add a KL penalty, which helps to avoid degenerate responses. So it keeps the sort of model that we're training with RL anchored to the original pre-trained model that produces this nice human-like language. And then we take this reward and we maximize it with PPO. So I want to just spend a few minutes talking about how does PPO work. I'm not going to go into all of the details here because there's a lot, but I'll try to give you hopefully an intuitive kind of quick sketch of how this works. So one of the sort of like fundamental approaches in reinforcement learning is called policy gradient. And this is the idea that you have, the gradient of your objective is equal to the expectation of your returns times the gradient of your log policy. So here's the returns and the gradient of the policy. And what this effectively does is it increases the probability of actions that will receive high return or reward and decreases the probability of actions that have low reward. So this is the sort of standard vanilla policy gradient theorem. There's a variation on it which changes this, return to a base or to an advantage, which is just the return minus a baseline. And this baseline could be lots of different things: a constant, a state value, etc. PPO uses learned state values, and just the intuition behind this is that you don't want to just use the returns as they are, from your environment. You want to perhaps like center them, make them a little lower variance. So here, like one example of this is, say the returns that you're getting from your environment are either 0 or 1. Then if you're just using the raw returns directly, in the case where this return is 0, you're going to have 0 gradient. And then you'll only be training on the rollouts that have return 1. But by subtracting off a baseline, we can turn the advantages into something a little bit more useful for training on. So this is the basic idea behind PPO. It has a whole lot of more bells and whistles that I'm not going to go into because it would, I think, take too much time that I don't have. So you don't need to understand the whole thing, but if I sort of gray out parts of this equation, you can see the same sort of like fundamental idea here, which is the policy and the advantage. And again, PPO learns a state value function online during training, so there's an additional thing you have to train besides the policy. And what that state value function does is it estimates what the future return is going to be in order to reduce the variance of the actual returns. So that's sort of a quick overview of PPO. And as I showed you, in this plot before, that works really well to improve the quality of the responses produced by the model over the pre-trained model. One trick that people sometimes use is to actually avoid RLHF together on PPO altogether with DPO, because this algorithm that I just described, where we have to learn this like value function alongside the policy, and we have to do this whole online RL loop. It's pretty complicated to implement. It's hard to get working. We have to, also like, deal with things like training a reward model, and then get into issues where maybe the policy over-optimizes for the reward model, and we have reward hacking, and so on and so forth. So wouldn't it be nice if we could just skip all of that? And that's the idea behind this algorithm called DPO, which stands for direct preference optimization, where they, again, I'm not going to go into all the details here, but they basically define a supervised objective that captures this notion of preference, where they define this what they call the implicit reward for winning responses and for losing responses, and they incorporate that directly into the loss, and that allows you to just do supervised fine-tuning without needing to do RL. And again, they find that this can work better than PPO in some settings. So the yellow here and here are DPO, and PPO is the pink, I think. Okay, so that's kind of an overview of the approaches that are often used in RLHF. Let's now switch gears and talk about RLVR, which, as I said, is RL with verifiable rewards. So a little bit of a history lesson before we actually get into RLVR itself. So there's this technique that was proposed a few years ago called chain of thought prompting, which basically addressed the issue that models are not very good at reasoning about things like math problems. And the way that chain of thought worked was rather than prompting the model to directly give its answer, so rather than just giving the number directly after receiving this question, you give the model these what are called few-shot examples that include some example reasoning traces in the middle. And that sort of primes the model into producing reasoning traces in its output before giving the final answer. And this really improves the performance of the model on math questions. Originally this was, I think, tested on GSMAK, but it also, works for like Hendricks math and more difficult math reasoning benchmarks. But the downside of this is like, we have to have these few-shot examples that are in domain for the particular task that we care about, which we don't really want for general purpose models. And like, if we want to try to increase, the quality of these reasoning traces, if we were trying to do this with SFT, we would need lots and lots and lots of these reasoning traces, which is sort of, hard to gather. So how can we, sort of sidestep this issue? And the insight of a number of papers is that, well, we can actually use reinforcement learning here. So again, if we have the prompt, this is the same question, we use that as the state. We sample the response, including the reasoning trace from the model, and then we get this action. And then this action is, the final reward or the final answer from this action, say 9, is something that we can just check with like string matching, right? If we have the gold answer, which is 9, we can check to see if that's correct. So that gives us our reward function, and then we can do RL with that. So there's 2 papers in particular that sort of like first introduced this idea in the offline setting. So that's STAR for self-taught reasoner and REST EM. This figure is from REST EM. The way that this works is you sample from the model using this COT prompting. You score each completion using a rules-based checker against the ground truth answer. You fine-tune the model on the correct responses, and then you repeat steps 1 through 3. And you can see here each iteration of sampling and then training the model, the performance increases a little bit. Now, DeepSeek R1 had the insight that we can go beyond this offline setting to the online setting by using online RL. And they use an algorithm called GRPO, which was actually introduced in an earlier paper of theirs from DeepSeek Math. And I showed you this plot before showing the performance increasing on Amy over training. They also found interesting things too, like if you give the model like a thinking budget for the amount of time it can spend producing a response, that also increases through the course of training. So how does GRPO work? So again, if we come back to this standard policy gradient reinforced with baseline idea that I talked about in the context of PPO, we can revisit that and sort of revisit some of the assumptions that PPO makes. So like I said, PPO uses a learned state value function to calculate these advantages. But if you look at, if we come back to this case, we said we were drawing multiple samples per prompt. And so we can actually use this insight to calculate our advantages. So this idea originally comes from this paper from Kuhl et al. In 2019, which has kind of a funny title, Buy 4 reinforced samples, get a baseline for free. And so the idea, though, is pretty simple. If you have like K samples, you just take the average of the returns across those samples and you subtract them off, and that gives us our advantage. And that's exactly what GRPO does too, with only a few kind of minor differences, like they divide by the standard deviation across the samples. They also, like, in contrast to PPO, they put the KL penalty in the loss rather than the reward itself. But otherwise, it's just the same sort of PPO loss that I showed you before, but using the advantages calculated in this way. And so, again, schematic, how does this work? You have the model, you sample your responses. Maybe some of them are correct and some of them are incorrect. We upweight the ones that are correct, downweight the ones that are incorrect, do RL, and hopefully by the end of RL, we are getting more correct responses than incorrect responses. So that's kind of a bird's eye view of how RLVR works. RLEF, again, RL from execution feedback, is actually kind of a special case of RLVR. But I wanted to sort of call it out separately because I think it's useful in the agentic setting. So let's consider the case where we have, some coding prompts and we want the model to be able to produce high quality code. Here's an example from the RLEF paper from Gehring et al. Of this year. And so, we prompt the model, we get it to produce some code, and then if we have some test cases that come along with this question, we can run those test cases and see if they pass or fail. And then we can use that signal of whether those test cases pass or fail as the reward signal, and again, we can train with PPO or GRPO. But the cool thing about the code setting is that because we're running this code in, say, like an interpreter or a compiler, we get actually some detailed feedback about whether or not, or like what actually went wrong, right? Like that might be something as simple as you passed 7 out of 12 test cases, but it might be something like there was a syntax error on line 12, right? And so we can actually use that feedback to reprompt the model and get it to make an additional attempt and then sort of put it into this multi-turn setting and do RL on that whole multi-turn setting. And we can extend this idea of execution feedback to tools more broadly if we consider that tools are usually implemented as, say, like Python function calls. So, if I might, want to ask the model, like, book me a flight from London to Neurops, and then ideally you would see the model use tool calls to say, like, okay, well, let me search where's Neurops located. All right, it's in San Diego. Let me find the dates, and then, like, search for the flight, and then recommend flights, and so sort of going back and forth between the text and the tool calls. Or again, in the code case, this is sort of more of like a Claude Code inspired example. We might have like, write me the unit test for the code in widget.py, and then it says, okay, I need to find where is widget.py. All right, here it is. Let me find what's in it. Let me look at that, and then let me write the test cases and run them, and so on and so forth. So this is sort of like the desired behavior, but how do we get there? So again, going back a few years, there's this paper called the React paper, where, similar to chain of thought, they introduced a prompting strategy for how to get models into a more agentic mode of behavior. So here they, again, using like few shot examples, you can prompt the model to first produce thoughts, then use do a tool call and get some feedback as a result of the tool call, and then reprompt the model again over and over and over to complete this multitask objective. I'm not really going to go into more detail here since I think there's a talk on agentic LLMs tomorrow, so hopefully that'll have some, some more interesting, explore some of the more interesting ideas in this space. But that's kind of the basic idea. And again, like now, like we did with, chain of thought, we can go from prompting to RL, and we can do the same thing with React prompting. And that's exactly the idea behind a recent open weight model called Kimi K2. Which sort of builds on the ideas introduced by DeepSeek R1, but then extends them to the agentic setting. And so they have like, a similar React style behavior loop that they use to generate behaviors. I think this is actually used for generating SFT data, but then they use that to sort of prime the model, and then they do RL on top of that. And the result is a model that is like significantly improved on agentic tasks over other open weight models and is comparable with some of the proprietary models too. Okay, so that's RLEF. And then I want to just very briefly talk about RLAIF, which is again RL from AI feedback. So existing LLMs are now like, pretty good at answering questions and doing instruction following and this sort of thing. So the idea here is that we can actually use them to provide judgments given a particular set of criteria or rubrics. And then these judgments can be used for RL training. So for example, we can prompt a model in the case of RLHF to say, pick the response that is more helpful. And we could define a whole bunch of like different criteria that we might want to use. And this is actually the idea behind the constitutional AI paper from Anthropic, which introduced this idea of RLAIF. And as far as I know, Anthropic still does this. They have, they publish actually Claude's constitution. You can go check it out here, which lists sort of like all of the principles that they ask Claude to consider in doing, RL training. But we can also use the same idea more for RLVR. So we can say, we can prompt the model to say, like, does this response like match this rubric or this ground truth answer or something like that? Okay, so that's the idea there. So we've sort of just gone through like these, 4 different types of reinforcement learning for LLMs. How do we actually kind of put this all together? So coming back to this, big picture, again, we first have this like SFT phase followed by RL. And in SFT, what we want to do is, get the model out of this mode of, say, requiring like few-shot prompting in order to produce its behavior and just have it do it automatically. So we can do this thinking and agentic-specific SFT. And this is sort of like the idea in Qwen 3. They introduced this idea of thinking mode fusion, where they use 2 different like chat formats in order to sort of prime the model to act in different ways. So in thinking mode, they have like thinking data that includes like reasoning traces, and then they also give the model this special like /think instruction. And so that will, by training the model on data that looks like this, gets it to produce, thinking traces before it answers. And similarly, in the non-thinking mode, you have this no-think instruction and then no thinking trace. And so they have both a combination of thinking data and non-thinking data. They train it with SFT on both of these. And then we do RL, which is a combination of all the flavors that I talked about. So as I mentioned, some models incorporate multiple SFT and RL stages. For example, DeepSeek R1 looks something like this. So we start with the DeepSeek V3 base model. We take some reasoning SFT data. In this case, they used 1,000 examples to sort of create this like primed SFT model that's in this thinking mode. Then we do RL on top of that. They didn't say how many prompts they used, so a little bit unclear how much RL they're actually doing, but they do RL. And then you might say that we're done, but ultimately, what we want is a model that can do both, thinking and non-thinking. So if you were to take this RL model and you ask it like, hi, it's going to spend like a minute thinking before responding to you, hi, and you don't really want to like have a model that is, spending that much time to just give you a simple response, right? So what they do is they use this RL model to generate a whole bunch of synthetic reasoning SFT data, 600,000 examples. Then they combine that with more general SFT data. They produce a new SFT model by, again, training from the base pre-trained model, and then they do RL again on top of that, and that produces DeepSeek R1. Qwen 3 is quite similar. The main difference being that they take the RL model and they continue training that to produce the second SFT model rather than restarting from the base model. But otherwise, the workflow is pretty similar. And like if you look at different papers, like the Kimi paper or like GLM 4.5 or whatever, there's sort of different approaches that different models use. But these are just 2 examples. Okay, so that's kind of the main idea. I want to take the rest of the time to talk a little bit about some of the open problems or interesting research questions that I think are kind of worth thinking some more about. So the first being, how do we improve the reliability of the tasks that we can already solve? So there actually was a recent paper from OpenAI just came out this week. And in this paper, they were asking, like, why do language models hallucinate? And the thing that they identified was that this actually comes from the way that we benchmark the models and the way that we train them, because we reinforce basically the model guessing, right? So here's like a toy example. If I ask the model, what month is my birthday? It doesn't know. But if it guesses, it has like an 8% chance of getting the answer right. If it doesn't guess, if it abstains, it has a 0% chance of getting the answer right. And so if we're just sort of rewarding the model based on what's correct, the model that guesses will be reinforced, whereas the model that doesn't guess will not be reinforced. And so this sort of like, encourages the model to hallucinate in these sort of like, exam style setup. And so they, have a recommendation for how to avoid this, which is to penalize guessing both in the evals, but also you could do this during training. For example, you could answer only if you are greater than T confident, since mistakes are penalized T over 1 minus T points, while correct answers receive 1 point and an answer of I don't know receives 0 points. So that's, one potential like solution to this. But, I think hallucinations are still like in my opinion, they're one of like the biggest things that we really have to get right in order to make these models more reliable. So I definitely think is like, worth spending time thinking more about this. Okay, another thing that we can do is, figure out how can we increase the difficulty of the tasks that we can train on. And I think this question really kind of comes down to a classic one in reinforcement learning in general, which is where does the reward come from? If you had been in the field, say like, 5 years ago or 10 years ago, you would know that this is like frequently a debate of like, okay, we can do RL, but like, what about tasks that we don't know how to produce a reward for? What do we do in that case? And I think that's still kind of an open question. So, we obviously can get human preferences, that's one type of reward, or we can have these verifiable answers. But what about things that are harder to verify? So for example, like a proof, like, I can ask a model to give me a proof and it will generate a proof for me, but how do I know that it's correct? Well, you might need to, say like, look at the proof and check each step by step, but now this is starting to get kind of expensive. And what if the model is sort of unreliable at checking each individual step? This is a hard question. And there's lots of examples that sort of have this flavor beyond just, like math. For example, like in coding, let's say you wanted to ask the model to do like a really big code-based refactor and train it to do this more effectively, right? Again, you can already ask Claude Code to do this, but sometimes it doesn't work. And you actually often, there's like, I think a common experience of using the coding agents is that, they do like a pretty good first pass, but then they have errors. And if you ask them to sort of like fix those errors, they can't really do it, right? And so, maybe we could use RL to train it to do a better job, but then like, again, how do we reward it to do that, right? We need test cases, and where do those test cases come from? And, like what if there's, not enough test coverage, and like then it's easy to introduce mistakes and so on and so forth. So not clear exactly how to define the reward in that case. Or like review my paper for any errors, inconsistencies, or flaws. I mean, this doesn't even necessarily have a ground truth. If you think about like human reviewers at machine learning conferences, famously very noisy process. And that's because like people disagree about stuff. People come up with different responses, different things that they care about. They pick up on different things. And so, there might not even really be like a ground truth here, but also like just human preferences, this is better than this, is sort of just surface level, right? It doesn't necessarily capture the detail that you would really require to train a model to do, better reviews. There's also maybe the time scale, right? So we could ask a model to design an architecture for a new social media app. But if we wanted to actually see how well is this app going to do, we have to build it, deploy it, get users, see how well it grows, and so on. It takes a long time, and we can't. That's too long to do this whole RL loop. So some things like the real rewards are just too long to really apply this type of method. And this is kind of more salient has recently been a big thing in the literature or in the news, like. Is how do you actually get models to optimize not just for like short-term advice, but in say like more long-term, for example, like therapeutic advice. There's been all of these like recent mental health issues with LLMs being sycophantic, and that's because RLHF optimizes for this sort of short-term like reward where is this response pleasing or not. And so the LLM will very happily like validate, what you're saying when it should be optimizing for your long-term health. So yeah, in all of these cases, this is, as I said, sort of this classic problem of like, where does the reward come from? And related to that is this idea of credit assignment. So if you recall back, to take GRPO as an example, we defined the advantages as like the return minus the mean of the return divided by the standard deviation across the samples. But what happens in the case where all of your samples are wrong? Then your advantages are going to be 0. There's nothing to learn in this case. So that's disappointing, right? Like now what? It feels kind of like counterintuitive. We should be able to learn something here, right? Like what if the agent had some good ideas along the way, like it sort of went in the right direction, but then went off the rails or whatever. And there has been lots of work actually on this area in terms of providing more like step-level credit assignment. So there's this term PRMs, some of you might be familiar with. It stands for Process Reward Models. And that comes from like these two papers, Iwasato et al. and then Lightman et al. This one's from DeepMind and this one's from OpenAI, looking at like training these like step-level reward functions and then being able to, score individual reasoning steps as, good or bad. But DeepSeek at least reports that this is hard to get working in practice, right? They say advantages are limited compared to the additional computational overhead it introduces during the large-scale reinforcement learning process in our experiments. So I think it's still a question like, how can we do this more fine-grained credit assignment so we're not stuck in this issue where, the samples that we get are all wrong and there's nothing to learn. Okay, and then the last thing I wanted to talk about is improving efficiency. So DeepSeek had this really interesting discussion in the R1 paper where they did this experiment where they took their 32B model and they trained it with RL, and then they compared that to a larger model that they trained with RL and then distilled into the 32B model. And what they found was that this distilled model was significantly stronger than the RL model. And so the conclusion from this is that, RL training with a big model and then distilling into a smaller model is better than just doing RL training on its own. But that is a little bit unfortunate, right? Because it means that we always have to train a bigger model if we want to have high quality small models. Ideally, we could get high quality small models without needing to train a big model first. So one question is, how can we make RL scale better for these smaller models to avoid the need to train such a big model in the first place? Another way that we might think about improving efficiency is a lot of models will engage in this thing that's called overthinking, where they try different strategies over and over to be extra sure that, of the answer that they're coming up with when, ideally way less thinking should be required. So this is an example from this survey paper. This is kind of a classic trick question for language models, which is larger, 0.9 or 0.11. They often get confused and think that 0.11 is bigger than 0.9 because it's 11 rather than 9, even though it's, a decimal. And so, the model goes in and it starts saying, okay, it's 0.9, but wait, let me check myself, let me check again, let me check again, let me check again, let me check again, and finally, it stops, but that's spending way more time thinking than it really needs to. And so how to reduce that and sort of think for exactly the right amount of time is again, a question. I have one other example of this overthinking, which is just a recent one that has been doing the rounds on social media, so maybe you've seen it, which is, so there's this sort of mass delusion about whether there's a seahorse emoji. There isn't, but many people think that there is. And so again, because models have been trained on the internet, they also think that there's a seahorse emoji. But then, because they've also, I guess, they're better than they used to be, right? So they realize that, wait, no, this is not the seahorse emoji. This one is the seahorse emoji. No, wait, it's not. Okay, it's a unicorn. Nope, that's a unicorn. Is this it? Nope, 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 nope. And it keeps sort of going on and on and on, and is, just gets really confused. And so this is actually a nice example of both hallucination and this overthinking problem. It's hallucinating because there isn't a seahorse emoji, so what's probably happening is that it's just guessing an emoji here. It's just hallucinating one. And it realizes it's not the seahorse emoji. And so it goes back and does this whole overthinking thing rather than just saying in the first place, no, there's no seahorse emoji. Okay, and then the final point is on sample efficiency. So again, those of you who maybe are familiar with more traditional deep reinforcement learning algorithms, there's been a lot of progress in that field over the last 10, 15 years. And the current state-of-the-art algorithms, things like Dreamer v3, are really quite good. So Dreamer v3 is an agent that can solve Minecraft, it gets all the way to the diamond at the end. And it's reasonably complicated. It's a model-based algorithm. It does off-policy learning with a replay and so on and so forth. But those sort of innovations pay off, and it's really quite a bit better than simple algorithms like PPO. And if you remember from earlier in the talk, like what do we use to do like RLHF? It's PPO, and even GRPO is like a just a variation on PPO. So I think if we look at like these types of results, we really ought to be able to do a lot better than PPO or GRPO. We're maybe just kind of scratching the surface with the reinforcement learning algorithms that are applied in LLMs. And in particular, I think that if we were to use like an off-policy, model-based, replay-based algorithm like Dreamer with LLMs, we might be able to train these models much more efficiently. So that's just a few food for thought ideas, research ideas. I think I went kind of fast through my talk, so I'm done. But yeah, that just as a recap of, we talked a little bit about pre-trained language models, and then how to do like supervised learning, this concept of LLMs as RL agents, and then different ways that we can do RL on top of them, how to put that together, and then some sort of like open questions. Just wanted to say thanks to Theo Weber, who shared his slides from M2L last year. I sort of adapted some of them for this talk. And I wanted to just point you to 2 additional resources if you're curious about this stuff. Nathan Lambert has this RLHF book, which goes into a lot of the ideas that I talked about. And also Kevin Murphy just released a new book on reinforcement learning, and that has a section on RL for LLMs as well, so you can check that out. So yeah, I'm happy to take questions. Thank you.